Welcome to our last video on TensorFlow basics, training, saving, and loading models. So far we've gone over the fundamental mechanics of TensorFlow, and now it's time to train our first neural network and learn best practices for saving our models in a way that makes retraining and serving them simple. In order to motivate the need for simple saving and restoring of our models, and in addition to showcasing what we've learned from previous videos, we'll begin with a full example of building and training a simple neural network. We will then learn proper usage of TensorFlow's new saved model builder to save everything needed to restore and use our neural network. Learning how to properly save and restore models can be daunting at first, but we'll save you time and show you the current best practices. Today we'll be exploring the question, can a neural network learn to predict random labels for randomly generated data? This is essentially the same question as, can a neural network memorize a training dataset, also known as overfitting? It is also something we can easily explore in a few lines of TensorFlow code. In the first slide here, I've defined typical values one specifies when using neural networks. The number of features is the dimensionality of the inputs. The number of classes is the number of unique predictions our neural network can make. The batch size is the number of training examples we feed to the network at each training step. And the hidden size is the dimensionality of the hidden layers. I've generated some random inputs for our network and associated random labels for each random input. And in this cell here, I've constructed the two-layer neural network we will be using. When someone says two-layer neural network, they mean a network with two hidden layers. The details of this should be fairly straightforward. For a given training step, we will set the input layer to be our input batch. Then each subsequent layer takes as input the output of the previous layer. Our output layer, which has num classes, number of nodes, is often called the logits. This is because it represents the unnormalized log probabilities for each class. And we move on here. You may be wondering why we didn't specify a softmax on the outputs on our output layer. That would give us the normalized class probability. The reason is because computing the softmax, particularly when doing so in conjunction with the cross-entropy loss, which we will do here, this can be computationally challenging, numerically unstable. So instead we use TensorFlow softmax cross-entropy as our loss function, which will handle the details of that for us. Note that we've defined a labels placeholder, which will contain the batch of fake labels for a given training step. And finally, gradient descent and backpropagation is neatly taken care of by TensorFlow's optimize loss function. I've chosen the Atom optimizer, which is a newer version of gradient descent that performs well in many scenarios. In order to see how our model is doing while it trains, I've defined a simple counter, numCorrect, that will output the number of correct predictions in a given batch. We could divide this number by the batch size to get the prediction accuracy for that batch. Here, I've added a few variables to a fetches and feeddict collection. This is actually a preparation step to make loading for our model easier, and we will revisit this in a few minutes after discussing the saving and loading methods. Finally, we train the model. As usual, we enter a session, initialize our global variables, then we loop over a predefined number of epochs. I've chosen 200. Since that was enough to illustrate the model was indeed learning the random data, feel free to increase that number and see how long it takes for you to reach 100% training accuracy. Now, before going further, it's important to provide an overview of TensorFlow's saving and restoring utilities. Before diving into Saved Model Builder, it's instructive that we understand how tf.train.saver works. This was the previous way of saving variables and graphs in TensorFlow before Saved Model Builder came out. In practice, we'll use a saver to save variables to a file. Remember that variables represent persistent tensors, and it's important to understand that saving variables is distinct from saving the graph. This means that before we call saver.restore, we are required to have already defined the entire graph. Now, the easiest way to remember how to use saver.restore is to think of it as initializing your variables with their saved values instead of initializing them from scratch. Although it's good to be familiar with saver objects, we now have a much more powerful way of restoring models, the Saved Model Builder. The Saved Model Builder, like the saver, can also save variables. It actually uses a saver to do this. But it also saves your graph, any named collections of variables you may want easy access to, and more. Specifically, Saved Model Builder allows us to save one or more metagraphs, as TensorFlow calls them, and it will organize the output contents nicely. It's true that a tf.train.saver can also export metagraphs, but Saved Model Builder has a cleaner user face, additional functionality, and is now the recommended approach by TensorFlow. In practice, we create a saved model builder as shown here, and we are ready to save our model we call add metagraph and variables. We can assign any arbitrary set of tags to associate with our saved metagraph, but I recommend choosing from the options in tf.savedModel.tagConstants. This one I've chosen here is training, which kind of indicates that I plan to use this model for training. Some other options are serving, for example, when you're trying to deploy to a production environment, which we will revisit in some of the more advanced sections later on. If we wanted to add another metagraph, we would then add more calls to builder.add_metagraph. Working with multiple graphs is a topic we'll also see later in later sections, but for now we'll focus on the single graph use case, which is by far the most common use case. Lastly, we'll call builder.save to write our serialized save model to disk. We can use the loader option when we want to load the entire graph and variables at once from scratch. This is extremely useful since it means that regardless of how complex our model may be, we can have a standalone file with only a few lines of code that loads the entire model from disk, giving us instant access to all variables in the graph. Let's see the process of saving or storing an action by returning to our neural network example. Seen in the slides, we create a save model builder once training is complete and call save. TensorFlow prints out some info that we haven't specified any assets, which is more advanced stuff that we'll see again as we explore through different use cases of TensorFlow. Assets is just things like, for example, you could have a vocabulary file, list some additional metadata information, but it's not really relevant for this example. It also shows where serialized save model protobuf file has been saved. Now let's see how to reload this file and continue training. Moving on. Now first we clear the default graph, since we'll be reloading everything from file again. This is only necessary since I'm in a Jupyter notebook. You would usually have the next cell in its own file and run it separately from the training program. So to load the model and continue training, we simply enter a new session, call the loader as seen in the slides, and that's it. Now our entire graph and all variables have been placed in the default graph, and we are ready to go. We can then enter another loop over some number of epochs and make the same calls as before. Notice how our accuracy doesn't restart at 20%, which is what it was before, but we continue where we left off and we make our way up to 47%. Remember, feel free to try more epochs, see how long it takes for you to reach 100%. Users that remember earlier versions of TensorFlow can appreciate the enormous improvement in simplicity this is compared to how things used to be, which we will not scare you with the details. We've reached the end of section 1. In just a few videos, we've gone over basic mathematics of machine learning and the core fundamentals of TensorFlow. Depending on your background coming into this course, this section may have felt very packed with information, because it was. If any video was unclear, make sure to read through the additional resources slide at the end of every video. In this video, we got a small sneak peek in the process of building and training a model. From here on, we'll be diving deeper into training more complex models and advanced usage of TensorFlow. As always, here's our additional resources slide for saving and restoring your TensorFlow models. Next up, computer vision. This is an area where deep learning has had tremendous success. In this context, when we say computer vision, we are most often referring to the use of convolutional neural networks for learning to make predictions on images. We'll work through detailed examples of creating and training such models.